Hey, so I just want to share a little bit of how my process works. I thought that would be interesting for some people. So I'm just going to jump right into it. I suppose, like, just to give you a little bit of background, I'm flying a drone over my neighborhood, and I'm using AI to detect all of the garbage on the ground, on the street and on the sidewalk, sometimes in the grass near the sidewalk. And then I'm using the precise GPS coordinates embedded in every drone photo to get an exact location of each trash or pile of trash in my neighborhood. And then I have an integration with San Francisco 311, which is like a way to report problems to the city that allows them to take action on those problems. I have an integration with that API, and I send the coordinates plus an aerial photo to SF311, which prompts them to come out and clean it up. And then I'm pulling every hour on the reports I make to see if there's a status update. So I'm going to jump right into the user interface here, which you're seeing right now. And just kind of want to show you how this works. So first of all, after I fly, I plug in the drone, I kick off an upload script, which automatically uploads all of the photos that I took, and sometimes it's around 1,000 photos usually. It kicks off an upload script that uploads all those to the cloud. In AWS S3, I have a completely custom application. You're seeing the back end of it here. And that kicks off an image processing pipeline that runs each image through a convolutional neural network, which detects if there's garbage in any of the photos. So like, for instance, the original photo that I'm sending up looks something like this. And the AI looks at that entire photo, and out of that whole photo, you can see it's identified that just right here, there's some garbage, okay? There we go. So, and here's another photo. We can look at this one. You can see out of this entire photo, it has detected that there's garbage right there. So we've got this whole photo, and it's found there's garbage on this corner here. Now this is interesting because on this photo, you can see that it didn't get everything. So it's missing this other piece of garbage here. So what I've built into my tool is sort of an ability to add or adjust these bounding boxes. I'm not going to do it on this one because this is actually just one for viewing it. But if I wanted to add this to my data set, I could do that. But I'll get to that in a minute. All right, so just to kind of have some FaceTime with you, the reason I'm showing you this is that I think it's pretty neat, and I thought maybe some of you would be interested in it. It's a tool that allows me to go from, to like control the whole pipeline. So I'm doing everything from like reporting, from detecting to like mapping and reporting where each garbage pile is, to like getting feedback from SF311. And then I'm also doing active learning. So when I find data that's off or really good data, I have built in some tools to adjust the bounding boxes and adjust what's been detected, and then feed that back into my training data set, which is a large set of images that are labeled already with the garbage piles and the image. And when I improve that data set, that gives me a better input to my training process for the AI detection, garbage detection model. So I'm essentially just continually improving. It's like continuous improvement on the model, and it is getting a lot better. And I think you can see like these detections are straight out of the AI. These are drone. I did these yesterday, drone to AI. So if we take a look at like one of these detections here, for instance, this one, and you look at what the drone actually detected, it looked at this entire photo, and in this entire photo, it found, let's see, 1, 2, 3, 4 piles of, or 4 garbage instances. Now it missed one over here, but look at this. It did a pretty good job on like detecting that's like some cardboard on the street. That's a small pile of garbage there, and then there's a little garbage bag there, or like an umbrella or something. Something shouldn't be on the ground. So it does a pretty good job. It's getting better. It's getting to the point where now like the detections are pretty reliable. Here's another one. So I just thought it'd be cool to see some examples. Okay, so here we go. So this one, see, it actually made a mistake. It did one thing right and made one mistake, and I'll show you that mistake in a second. But here's one thing it did right. It found there's a lot of garbage around this garbage can here. And sometimes the AI makes mistakes, and that's expected. It's going to take time for it to converge on a very reliable result. Because every garbage pile is a little bit different. Garbage is kind of unique in the object detection world, where like a human face, like even though we're all different, we have some commonalities that are pretty easy to identify, like the sort of like layout of our face with eye sockets and nose and mouth and chin and forehead and ears. Like there's a layout to a face that's consistent. Whereas like garbage piles, if you look at how they're configured, I mean, this is not the layout of every garbage pile. It's not as obvious to like determine this is a garbage pile to the AI, because every garbage pile is a little bit unique. And you can see that if you look at this page. So like here is a garbage pile, and here's a garbage pile. Here's a garbage pile. They're different sizes, different colors, different sort of layouts. So, however, the AI has been able to find features that it can look for to determine if something's a garbage pile. It's getting a lot better when I put more data in it, is what I'm trying to say. So the more data I put in, the better this model gets, because it gets at least, for each different type of garbage pile it could see, it's going to gather at least, some number of examples that it can then use in the training data to adjust, to like find the right weights for that window, for that like filter. I guess it takes a little understanding of how a convolutional neural network works to kind of grok that. Let me talk about that for a second. So a convolutional neural network is different from a neural network in that it convolves a filter or a kernel over the entire image. So it takes a kernel and it sort of scans it across the image like this. So it's scanning across the whole image. And in that kernel, say it's like 5 by 5 pixels or 10 by 10 pixels, there's multiple different kernel sizes and multiple different layers, and each layer has a different number of kernels, and they're connected in different ways to other layers. Forget about all that. For the moment, just think about one layer and one kernel. It contains, let's say, 6 by 6 weights for a 6 by 6 pixel kernel, so it's 36 weights. Each weight is randomly initialized to some random number at the very beginning of a training cycle, and then as we know where the garbage is. So as the kernel is scanned across the image, when it gets the answer wrong or right, we're going to adjust those weights with something called gradient descent and backpropagation. But forget about that for the moment. But we're going to, in our training algorithm, we're going to adjust the weights in that kernel so that they move closer to what they should have been in order to have gotten the right answer. So in some cases, the right answer is that is not garbage. And in some cases, the right answer is that is garbage. And if you do that enough, the weights in that kernel start to sort of converge on some feature. That feature could be the shininess of a garbage bag, or the ridges of the garbage bag, or it could be the sort of like dispersion of like loose debris. It could be something in like the texture. And here's the thing: is texture is really important, actually. So it's been found through research that convolutional neural networks and neural networks in general, when they're used on images, tend to be biased towards texture versus shape. So, for instance, like the texture of your eyelashes or the texture of your nose or forehead or the texture of a beard. Those are the things that the different feature portions, the convolving kernels, pick up. Now there is another layer that combines those kernels, and that is a fully connected layer, which then takes the different kernels and says, well, when they're the different like filter, the different features that are detected with the kernels, and it combines them. It says if you find an eye here and an eye here and a mouth here and a nose here, that's pretty likely that you have a face. In the garbage pile, that fully connected layer, it's a little different because like there could be a garbage bag and loose debris here, or there could be a loose debris here and a garbage bag here, or loose debris on top of the garbage bag or under the garbage bag. Like it could be anywhere. There could be loose debris all around the garbage bag, or there could be no loose debris. And so there are many more conditions and many more configurations of garbage, and that fully connected layer is the one that probably has difficulty. Whereas like understanding the texture of a feature in a garbage pile is probably just about as easy as understanding the texture of a feature on an eyeball. There's a shiny part, there's an eyelash fuzzy part, there's a skinny part around it. It's like the skin texture. And whereas in a garbage pile, let's go take a look at one. You can see that there are textures here too. There's like this garbage bag texture, which is like this white garbage bag where it has like sort of like crinkles and edges and ridges and sort of lots of shadows. And then there's like this loose debris texture, which is more of like it's a bit more color, but the texture is like this like bump, is almost like a bumpiness, like a ridginess. So there's like, and then there's like the box texture, which is like a flatness. There's like flat sides to it. So yeah, I don't know how to really describe these textures in the way that a neural network sees them, but I think there are consistencies in the textures. It's just that they're arranged in a different way than on every pile, essentially. But if you look at enough piles, you're going to find patterns. So let's look at these two piles here in the bottom right-hand corner. So there's white debris and black garbage bags. And they're next to each other. So like whether they're below, above, or to the left of, or to the right, is less important, but the fact that they're next to each other, that kind of constitutes a pile. So that could be one form of pile. So you might find that one here. Maybe there's this one over here on the right now, the one on the left here. This one could fit that pattern, and so on and so on. Maybe even this one here. Maybe you can substitute loose debris for cardboard boxes, or maybe it's like the grate underneath this one indicates that could be garbage. That's probably not a great feature, but I think it may be the case that that's being taken into account because there are a lot of garbage piles on those drainage grates. So you can see some consistencies in the pattern. All right, so I'm going to show you now what it looks like when I find something that shouldn't have been detected as garbage, that I need to sort of teach the model how to do better on. So I'm going to look at unprocessed data, something that I haven't filed, that I didn't file, and I'm going to use my confidence threshold, and I'm going to set the confidence threshold between 60 and 70 because I'm not even looking at anything below 60 in my model. Like I probably should for training purposes. I'm not. However, like things that are between 60 and 70, sometimes they're not actually garbage. And that's a good place to get started with a little bit of training. So here's a good example right here. And I think I've already corrected this one, so let me find one that I haven't corrected. Here we go. So see this one here? This is rock. This is not garbage. So let's go take a look at this one. So if we look at this, it's definitely rock. What I'm going to do is I'm going to click this training beaker. That training beaker is going to add this detection and its bounding boxes into my data set. And then this gives me the opportunity to see all the bounding boxes it detected. So it did some of them right, although maybe that's like a little misaligned. And did you see what I did there? I just adjusted the bounding box. That's what this tool allows me to do. And so here, oops, I accidentally drew a new bounding box, a little tiny dot. So this one here, maybe it needs a little adjustment. Maybe I widen this a little bit. You know, these are little mistakes that can be sort of tweaked. Maybe I wanted to consider that as well. And then here, I don't think it should detect that at all. And this is really powerful to add these negative examples into the data set to teach the AI, hey, that's not garbage. Do not consider that garbage. It takes a significant number of those to really overcome some of the false positives you might get early on, but you will, if you keep adding them, eventually improve your model. And that's what's happened with my model. It's gotten a lot better. There are things that it used to detect all the time that it no longer detects. So what I did there is I just clicked a keyboard shortcut which approved this image and its manifest file, which contains all of the bounding boxes data, and it approved it to add it into my data set. So next time I build a data set for training, that will be in the data set. There are other things here, like this one here, like that's not garbage. It just thinks that maybe these street signs or something are garbage. So let's add this one, or these like little like road, I don't know what those are called. Yeah, so it does. See, it thinks these are garbage, but they're not. So we're gonna remove them. I just hit a shortcut key to delete that from the data set. And then we're gonna adjust that one a tiny bit. This one, it thinks these are garbage again. Oops, I added another tiny little data set point. I don't want that in there. Okay, so now that looks better. Okay, so now we have one detection. You can see the number 1 there. And that's good. So I'm going to close all the rest of these ones down that I've been opening up just to neaten up a little bit. And we can go down here and look for more negative cases. Here's a negative case. So I can usually just filter these out like by setting the threshold above like 70, even above. Sometimes I start with the threshold above 98% confidence, and that gives me like really great results. But like going back and looking below the threshold for examples where it made mistakes helps to improve the model. So here's the example. It thought this pillar was garbage for some reason. So, you know, maybe it looks like a cardboard box. I don't know. I'm going to do that. But it also missed this little pile of garbage here. And it missed these. I mean, these are pretty small. I think that the texture is interesting on this. So I'm going to add them. So now I have 4 data points, and that means I'm not looking at one of them. Here it is. And it made another mistake here. So it thinks this garbage bin is a garbage pile, and it's not. It missed this. So this is a really good negative example where it's made some mistakes, and it gives me an opportunity to add new data to the data set that improves the results in the future. All right, so when I'm done with all that, I have a button up here, a little beaker at the top. When I press that beaker, it's going to create a new manifest file. And if I sign in to my console, Oops. Now I'm going to be able to go to S3, and in S3 I'll be able to find the manifest file. Manifest. So it's just created a new manifest here for April 1st. There it is. So that's the new manifest file. I can basically copy the URL of this. I can go to recognition, and I'm going to train a new model based on this here, based on this annotation. So projects, this is my model that I've been playing with. I'm going to go to the data set. What I've been doing is just to keep I like to not have to change too many configs, so I just go here and I delete the old training set. This is not deleting the manifest, this is deleting the recognition version of the data set. So it's like I still got the core data set in the S3 bucket. So here I'm going to go here and I'm going to import this new. So I deleted the testing data set, I deleted the training data set, now I'm going to replace it with the new version, which is in the format of SageMaker Ground Truth. It's a file format that includes JSON lines, and each line describes a image with its bounding boxes. And then I'm just going to put the S3 URL here, click Create Dataset. Now it's going to import all those data labels. There's probably like 12,000 labeled garbage piles now into this thing here. And what we've got is a data set. So this has 10,760 labeled piles of garbage in it. And you can kind of go and look at these if you want here in this viewer. I don't like Amazon's viewer, that's why I created my own. And then I just click Train Model and kick it off. Okay, so it's going to take a little time though. That's going to take some time. It's starting by distributing the data set between a training and a testing set. And it's going to it's going to kick off the model. It's training in progress, and soon we'll have some results. So that's that. That's how that works. Now, next time I use my site here, I'm going to take advantage of the new model. As long as I'm going to check the model to see if it actually performs better. So you get with each model some like metrics. So you can see here like a little progress and like improvement. So this one had an F1 score of 458. Then a few days later I got 462, and then a few weeks later I got a 466. So hopefully this new one goes even higher. That's an F1 score. It's okay that it's below 50%. In fact, I found that even though my precision on some of these models isn't even 50%, and my recall isn't 44%, it's okay because when it's off, it may just be that the bounding box is a little bit off from where it needed to be. It's not perfectly aligned. And that's because each garbage file is very unique. It can be very tricky to get a perfect bounding box. Also, like, there are still false positives. And there are garbage piles that are unique enough that it doesn't have enough examples to catch them. So even though my training set still includes some of those, I think that the larger my data set gets, the more examples I'll have, and the better this model will do. Now, I may eventually find that I need to use a better architecture, a better model architecture. And in that case, like, it may just be that I don't have enough fully connected layers, or I don't have enough convolutional layers to account for all the variations that are possible. That's something I'm interested in doing. A little secret, I've applied for National Science Foundation grant funding to do some research around improving the model using a technique of adding more data, but also tweaking some of the hyperparameters and maybe even tweaking the architecture of the model itself. Right now I'm just using an out-of-the-box model. I don't even know what Amazon is using. It's probably using like a like a RCNN or some other very common ResNet-based convolutional neural network. It doesn't tell you, but I have tried ResNet. I've tried other models like YOLO, and I've also tried some mask data sets, like mask RCNN, and the results have been similar. They were actually a bit better when I did it on my own, but not it's still performing fine given these metrics. So yeah, let's see which one. I think I have some here that look like they're performing really well, but it turned out I had data leakage. So on this one that has a precision of 874, I had some data leakage, where some of the data that was in the training set leaked into the test set, and so it looks like it's doing better than it is. So you can take one of these models and you can go and view the test results and see like how it did. So for instance, on this one, it was very confident for this false positive, number 1. You know, this tool is really bad, honestly, this Amazon tool. Like, look at this. Like, there's no way to actually make sense of this because it's just like, I can't tell where, I think number 1's up here. But like number 0 was a true positive. And like, you know, honestly, a lot of this stuff probably is garbage that maybe I didn't have labeled. So that's one of the other things. It's like, is my data set perfect? No. So like these numbers, this F1 score, it's more of a relative measure than it is an absolute measure. So like I've heard people asking like, how high of an F1 score do you need to use a model in production? And I tell them like, and what I think to myself is that it's use case by use case, and it depends on how you're using it. Not only like what you're using it for, but how you use it. In my case, I have a man in the middle who's me, who's looking at all the detections. So precision and recall are important, but they're not absolute. And really my measure is like, how much time can I save myself from doing it from pure manually to doing it AI assisted? And then each week, how much time can I save myself if I improve my model? And what I've found is that like as my model improves, even incrementally, even in small increments, it saves me time. Because then if I filter like the 98th percentile, you know, I'm getting a higher majority, a higher percentage of them are things that I would report. As you can see, machine learning isn't just data science. It's not just spending time in a Python notebook. It's not just theoretical thinking or theoretical work. There's a practical aspect to it. And I think that's important to consider when you're building a model. How are you using your model in the real world, and how do improvements to your model change your performance in the real world? How can you take real world examples of results from your model and feed something back into your training process to improve your model? You can see what I've done here is to implement my own system, which I think is better than AWS's, for my purposes at least, of improving my model by feeding these things back in to false detections, feeding them back into my model. And I just make a practice of every time I fly, I will go find some data that I can use from that flight that I can use to improve my model a little bit more. So it's a little bit later in the day, and the model has finished training from earlier. I also just did a flight and accumulated a whole new set of images, which are being processed at this moment. But yeah, I just wanted to show you the model and how it's improved. So if you look on this line right here, just to the right, April 1st, this has gone from what was previously a 0.466 F1 score to a 0.473. And 0.473 with a precision of 0.541 and a recall of 0.420. That's also with a pretty low threshold. So I could up that threshold and get more reliable results. And then previously our precision was under 5. So you can see it's a marked improvement, and that was just by adding more data. So yeah, I just added more data, got a better result, which is really awesome. So super happy to show that. So there you have it. Thanks for watching. And if you like this channel, be sure to subscribe. I really want to get to the point where I can monetize this channel, and I'm not there yet. I need 1,000 subscribers to monetize. So yeah, if you like it, tell your friends. I'm going to try to produce more content for people who want to make stuff with AI, who want to build practical applications with AI. And I'll see you next time.